So this is equation 6b. Okay. So let me check. Yep. Right. So that's it. Okay. Just integrate 4 times. Very, very straightforward technique. Okay. To apply this technique well, a very critical point to take note is your boundary condition. All right. If you don't know your boundary condition, okay, you're done. Okay. This technique is as good as useless. Right. So as I mentioned before, we can use this to solve, right? We can use this to solve, we can use this to calculate the slope, right? The slope and the deflection of the beam. Okay, so we can determine the slope and the deflection of the beam. So I'm going to introduce another problem. Okay, I'm going to introduce another problem. Example number 2. So we have seen the abilities, right? Before I go to the problem, we have seen the abilities that is used to solve for determine the slope and the deflection of the beam. Okay, so the next thing we're going to do is we're going to look at can be used to analyze statically indeterminate structure. Okay, that's how powerful this technique is. So example number 2. Okay, we're going to look at example number 2. So example number 2 is a cantilever beam. Okay, so we have a cantilever beam. Then we call this point A. So point A, the structure is on a set of rollers. Okay, we have a set of rollers over here, and point B is built in, and point C is somewhere in between, and at point C we have a evenly distributed load. Okay, and this distributed load is omega. Okay, and it's in Newton per meter. Or does not need to have a unit. Okay, so we're going to call it omega. And then on our x-axis and on our distance to point C is L/2, and from here to here is also L/2. Right? So we want to find, okay, we're going to find the reaction at AY. Okay, we want to find the force at AY, and we're going to draw the bending moment diagram. Okay, we're going to draw our bending moment diagram. And as you can see, this structure is statically indeterminate. Okay, so note that the structure is statically indeterminate. So why is this structure statically indeterminate? I'll show you, okay? Because some of you might recall, some of my I can't remember now. Okay, so why is it statically indeterminate? So if we were to draw the free body diagram, all right? If we were to draw the free body diagram, we have a load over here, right? This is your AY, and then so this is your point A, point C, and point B, and over here you have a load coming down, right? And this load is omega L divided by 2, right? So we know that over here, we are going to have a By, right? And then because this beam is at point B is a cantilever beam, right? It's a cantilever beam. So I'm going to assume that the moment at point A, at point B is going in that direction. Okay. So if we're going to use static analysis, so how many unknowns we have? Okay, so unknowns is AY, BY, and moment about point B. Okay, so let's say, okay, we want to apply static analysis. So you're going to apply static analysis, right? So you say, okay, we can do summation about forces. So let me draw our transformation first. This is X, Y, rotation about Z. Okay, so summation about forces going up in the Y direction is equal to 0. So you have AY plus by BY minus by omega L over 2. The whole thing is equal to 0. So this is your equation A. Okay, and then you say, okay, right, fine. I'm going to take moment about point A. Okay, so we're going to take summation about moment Z. Okay, I'll change my mind. I'll take point B. Okay, so now this is equal to 0. Okay, so we have what we have is so now we are taking our moment here, right? So it's anti-clockwise. So moment about point B, then plus by omega L over 2 multiply. So this distance from here to here is omega. Oh no, omega what? It's L over 4 because it's evenly distributed load, right? Then you have minus AY L. The whole thing is equal to 0. So you have AYL, right? AYL is equal to moment about point B and plus by omega L squared divided by 8. So this is your equation B, right? The next thing you do is summation about forces in the X direction, which is going to give you equal to 0, right? So what you will see over here, you have unknowns. You have AY, you have BY, and you have moment about point B. Okay, so you have 3 unknowns with 2 what equations. So this is impossible to solve. Okay, I mean impossible to solve in a normal way without using numerical methods, for example. Okay, I know with numerical methods you have 3 unknowns, you have 2 equations, go and have fun. Okay, but we are without that, right? So we realize that, hey, this structure, so from here we say that the structure is statically indeterminate. It's not a bad thing, okay? Statically indeterminate structure does not mean it's a bad structure. It's just statically indeterminate, okay? It's not say, hey, this is not a very good structure. Nothing to do with it, okay? Don't think about that. Okay, so we're going to solve this now, okay? We're going to solve this now. So if we, okay, so we're going to apply the elastic curve method. Okay, we're going to apply the elastic curve method. So from here, we draw our diagram again, or I'm going to copy from here. Yeah, I'm going to copy the whole thing. right? So we are going to call on the left hand side x equal to 0. On the right hand side, x is equal to L, right? So we again V M theta y V M theta y. Okay. So we know that at x equal to 0, M is equal to what? 0. Okay, because when you remove the support at point B, the whole beam will rotate, right? And we know now the boundary condition states that y is equal to what? 0, right? We know that. Now on the right hand side, which is cantilever, M is no more a 0. Okay, so we don't know what is our V. Moment is not equal to 0 because it's a cantilever beam. Right? Why do I say moment is not it? We don't know, because if we remove the support at A, what will happen? Will the beam rotate? The answer is no. The beam will not rotate because it's in a cantilever beam. Okay, but we know that the slope is equal to 0. The y is equal to 0. Now, some of you might ask me, hey Eugene, why this is the case, right? So why that is the case? So I'm going to stop. Can you all see me in a bigger sense? Yes or no?
Yes.
Okay.
Yes.
So you can see my ruler now, right? You can see my ruler. So where my fist is now, right, is where is a cantilever is built in. Okay. The other hand, my flat palm is the load, right? So when I push it down, you can see the deflection goes on, right? But I want you to look at the angle, the slope down here at my fist. Okay, there's my fist. I want you to look at the angle. What is the angle equal to? Can anyone tell me?
45.
0.
0.
Yeah.
Right? If you look at exactly at where my palm is, okay, when I bend it, it's equal to what? 0. The slope is equal to 0. Further away from my palm, you have a slope. Yes or no? You see a slope now. Yes? Okay. So when that's the case, right? When this is the case, right? That's why we call this is equal to what? 0. Right? Now, what I'm trying to tell you is this. Do not memorize whatever I teach you. Do it physically if you can, okay? If you're going to memorize this, good luck, man, okay? After next week, okay, August, the whole month of August, you will forget everything. Okay? There's nothing to remember. You just need to observe what? Physically. There's nothing to remember. You just need to observe physically, okay? So that is why when it's cantilever beam, theta is equal to 0. Okay, so we know our boundary condition. So we know that, so how many boundary condition we know? So boundary condition number 1, boundary condition number 2, boundary condition number 3, boundary condition number 4. Okay, so we know the 4 boundary condition. Okay, so we also can foresee that we can get 4 unknowns. Okay, let's see, do we actually need all of them? Okay, so for this case, right, due to simplicity, I'm going to apply, okay, we're going to apply positive shear or not positive, we're going to apply positive bending moment okay, bending moment. Come on, Eugene, wake up. Okay, bending moment to find the bending moment equation. Okay. I'm not interested in the shear force because I no need to form the shear force equation. Okay. Once you have the bending moment equation, we're going to use what? The elastic curve already. That's why